In school, we learn all these scientific laws that seem, well, perfect, absolutely set in stone. But what if I told you that one of the most fundamental laws you learned in chemistry is actually built on a really fascinating flaw? Yeah, let's get into it. Oh, yeah, you definitely remember this one. PV equals nRT, the ideal gas law. It's clean, it's simple, and it's supposed to describe how a perfect or ideal gas behaves. It's kind of the gold standard we all learn first. But that's the thing, right? The key word is ideal. And in the real world, things are almost never perfect. So, what happens when this super clean, simple law smacks right into messy reality? When does it just break? Okay, so to figure all that out, scientists needed some way to measure just how far off a real gas is. They needed, like, a reality check. And that reality check has a name, the compressibility factor. We just call it Z. You can think of it like a report card for a gas. It's just a simple ratio that compares a real gas's volume to what the ideal gas law predicts it should be. It's basically our non-ideal behavior detector. So, for our imaginary perfect ideal gas, that score, that Z value, is always, and I mean always, exactly 1, no matter what. It follows the law perfectly. Zero deviation. But when we look at real gases, the story gets way, way more interesting. Their Z values are almost never 1. They dip down below 1, then they curve back up and shoot way above it, especially when you start cranking up the pressure. This is the smoking gun, right here. This is the proof that the ideal gas law is failing. So this gets us to the big mystery. Why? Why does reality stray so far from our perfect little model? Well, it turns out the ideal gas law is built on two huge assumptions that are, well, let's be honest, they're just plain wrong. So let's dig into the first flawed assumption. It's one of those things that seems so obvious once you point it out, but the ideal model just completely ignores it. Right. So the ideal gas law basically pretends that gas molecules are just these tiny little points floating in space, that they have zero volume, which is, kind of crazy. In reality, of course, molecules are actual physical things. They take up space. Here's the perfect way to picture it. Think of a giant empty dance floor with just a couple of dancers. Their actual size doesn't really matter, right? There's plenty of room. That's like a gas at low pressure. But now imagine that same floor is absolutely packed. It's shoulder to shoulder. Suddenly, the space each person takes up is crucial. You can't ignore it. And that's exactly what happens to a gas at high pressure. The volume of the molecules themselves becomes a huge deal. Okay, so that's flaw number 1. Molecules have size. Pretty straightforward. But let's look at the second one, because this is where things get even more interesting. It's all about a force the ideal model just pretends isn't there. The second huge assumption is that gas molecules just zoom around, completely ignoring each other. No attraction, no repulsion, nothing. But we know that's not true. In the real world, molecules actually have these subtle forces of attraction between them. You can think of this attraction like a tiny bit of gravity between them. It pulls the molecules a little closer together, which means they don't smack into the walls of their container quite as hard or as often. And what does that do? It results in a lower pressure than the ideal law would predict. This effect really kicks in at lower temperatures, when the molecules are moving slower and don't have enough energy to just zip past each other. So let's recap. We've got two major problems. Molecules take up space, and they attract each other. Our ideal gas law is officially broken. So how do we fix it? We need a smarter equation. And this is where a guy named Johannes van der Waals comes in. Way back in 1879, he came up with this absolutely brilliant modification. Now, I know it looks a little scarier, but it's actually an incredibly elegant fix. The van der Waals equation just takes our good old ideal gas law and cleverly adds two little correction terms, one for that molecular volume and one for that intermolecular attraction. And it's really simple how it works. See that constant A? That's our fix for the attractive forces. And that constant B? That's our fix for the physical volume the molecules take up. Each correction term directly addresses one of those flawed assumptions we talked about. Problem meets solution. And what's so cool about this is that these correction factors are different for every single gas. They're like a unique fingerprint. So you can see here, tiny little helium has super low values for both attraction and volume. But a big, beefy molecule like carbon tetrachloride, its values are way, way higher. The equation is actually tailored to the gas you're working with, which makes it so much more accurate. So what's the big lesson here? What does this all mean?
It's that scientific models are these incredibly powerful approximations. They're designed to simplify the messy real world to make it understandable. But we have to remember, they are not a perfect description of reality itself.
And this tells us the most important thing. You have to know when your tool is the right one for the job. That perfect, ideal gas law, it works great when its flawed assumptions don't really matter, at really high temperatures where molecules are flying around too fast to attract each other, and at low pressures where they're so far apart their size is irrelevant. It only really starts to fail when you push things to the extremes, super high pressure or super low temperature. And that kind of leaves us with this final, bigger question. We just took apart a law that seems so fundamental and found this whole other layer of complexity underneath. So it makes you wonder, what other scientific rules that we take for granted are also just the starting point, just the first simplified chapter of a much deeper, more fascinating story?